It should have shattered, but the first frame after the sun said otherwise. For 2 weeks, 3I, Atlas, slipped behind the solar glare, exactly when heat and radiation were at their most punishing. When observers began reporting post-perihelion views in mid-November, the story many expected debris and multi-nucleus breakup didn't show up in public data summaries. There is, as of now, no official confirmation of external fragmentation. Major agencies continue to describe 3I, Atlas, as an interstellar comet on a hyperbolic path, with a nucleus constrained to a range of roughly 0.445.6 kilometers from Hubble analyses. That framing, natural, not technological, intact as far as current public evidence shows, remains the responsible baseline. One result is especially clarifying. Radio astronomers using South Africa's Meerkat array detected hydroxyl OH at 1,667 MHz, the classic 18 cm water proxy that appears when sunlight breaks H2O into fragments. That is not a spacecraft transmission. It's chemistry. Multiple reports converged on the same reading. An OH absorption, line detection tied to cometary outgassing as 3I, Atlas, neared the Sunday. This single detection does not solve every puzzle, but it firmly anchors the narrative in natural comet physics. If a single frame can kill the certainly exploded storyline, it also opens better questions. First, why did the post-sun morphology look tidy? In true breakups, we tend to see multiple condensations inside one diffuse envelope, string of pearls features, and irregular brightening. A useful contrast exists right now. Comet C, 2025, K1, Atlas, a different object that merely shares the Atlas survey name, was imaged with a broken nucleus and complex debris structure after perihelion. Several outlets and observatories showed clear, multi-blob evidence. That is what confirmed fragmentation looks like. The fact that comparable, multi-nucleus signatures have not been publicly confirmed for 3I, Atlas matters for how we write the next chapter. Second, what about a tail that appears to point sunward? Did the comet break the rules? No, that optical illusion has a well-understood name, an anti-tail. It happens when large, slow-to-respond dust grains spread in the comet's orbital plane, and the observer's viewpoint crosses that plane. Geometry does the rest. This has been modeled and observed for decades. Classic analyses by Zdeněk Sekanina and others formalize dust dynamics, gravity plus radiation pressure, that can yield a brief, striking anti-tail without any exotic physics. In other words, 3I, Atlas, showing sunward structures at times, is consistent with known comet behavior plus viewing geometry. Third, and this will drive the film's middle acts, what's powering it? The energy budget debate isn't tabloid fluff. It's a real, testable question. If a small nucleus puts on a big show, perhaps the active area is larger than we assume, for example. Internal fracturing that multiplies vents, without obvious exterior splitting, or the composition skews toward more volatile ices, or our size, flux inferences need refinement. The scientifically productive way to treat the mismatch is to instrument it, not mystify it. Get spectra for H, 2O, CO, 2CO ratios. Repeat the OH measurements in different circumstances and tighten astrometric solutions to isolate any non-gravitational accelerations. The OH line already tilts the scales toward ordinary cometary outgassing. The rest is a matter of stacking measurements over time. Here is the part the public needs clearly, up front. The upcoming big date is not a scare headline. The best widely cited geometry window is the 19th of December, 2025, when the Earth-comet distance is about 270 million km, roughly 1.8 AU. That is far. It's valuable not because the comet passes near us, but because the observing geometry and signal-to-noise are favorable for follow-up spectroscopy and imaging from multiple longitudes and instruments. Both ESA and NASA summarize this plainly, and independent astronomy media echo the distance and timing. This is an opportunity to measure better, not a reason to panic. To be precise about the what we know pile, 3I Atlas is the third confirmed interstellar visitor after Oumuamua and 2I Borisov. It travels on a hyperbolic orbit, unbound to the Sun, Hubble-based constraints place the nucleus between a few hundred meters and several kilometers, and we have at least one robust radio detection of OH. These are not rumors, they are institutional summaries and peer, preprint tracked results the audience can verify. Each point narrows the room for fanciful interpretations without shutting the door on legitimate physics puzzles, like how active area, jet directionality, and grain-size distributions interplay to make the anti-tail so persistent. On the other side sits the temptation to romanticize anomalies. High-profile commentary has speculated about thrusters and navigation jets. In a storytelling sense, those lines are candy. In a scientific script, they belong in a clearly labeled drawer. Hypotheses that demand extraordinary, discriminating evidence, for example, exhaust speeds or line ratios incompatible with sublimation physics, controlled pointing behavior, or radio structures unrelated to known cometary chemistry. Absent such signatures, the natural comet reading with an anti-tail, explained by geometry, and an OH line explained by water, remains the most economical account. The audience deserves that hierarchy. So our opening movement resolves like this. After the sun, light returned, and the it exploded. Verdict didn't. The radio line said water, not message. The tail that sometimes seems to point at the sun has a decades-old explanation in dust dynamics and viewing angle. And the genuinely interesting tension, the energy and activity budget, now has a calendar. December 19 is when geometry helps us test it better, not when danger arrives. That is the mood of this film. Rigorous, calm, and verifiable. Breathe with that for a moment. The sky went silent, then it didn't. The frame after the sun gave us less drama and more work. Count the molecules, weigh the jets, track the motion, and let the lines and light speak in numbers the audience can check. We will keep the recurring motif, light, silence, memory, breath, because it matches the science. Light returns. Silence becomes a datum. Memory is the logbook we write. Breath is the cadence we keep while the instruments do their part. The next sections will widen the contrast with C, 2025, K1S confirmed breakup, and then dive into the geometry and energy math that make 3I, Atlas, feel unfamiliar without breaking the rules. For 2 weeks, the sun erased it from our view. There is a kind of silence that isn't empty, it's blinding. In late October, 3I, Atlas, slid too near the solar glare to track cleanly from Earth. The timing hurt. This was the exact stretch around perihelion when heat, radiation, and outgassing forces peak when a fragile nucleus is most likely to fail. From the ground, though, the sun was a lid. The line of sight ran straight past the solar disk, and the object vanished into brightness the way a whisper disappears into surf. That geometry has a name: solar conjunction. It's a regular, well-understood cause of observing blackouts for planets, comets, and even spacecraft communications, not mystery, just optics and the sun's power to drown signals. So our test happened offstage. The comet met the furnace. We stared into white. For storytellers, that gap is torment. For scientists, it's the difference between prediction and memory. All the pre-sun models said a loosely bound, volatile-rich rubble pile could crack, spin up, or shed a chain of fragments under the thermal and jetting stress. And then, nothing we could see. We were left with equations cooling on the page, waiting for light to come back. A few anchor facts keep this section honest. First, 3I, Atlas is unbound, an interstellar comet on a hyperbolic path, not a periodic visitor hiding behind the sun to surprise us later. That status comes from institutional summaries and Hubble-based imaging that tracked the object's motion and morphology earlier in 2025. Second, independent agencies were watching from every angle they could, before and after the glare window. ESA even leveraged a different vantage. The ExoMars orbiter pointed at 3I, Atlas from Mars in early October, bracketing the timeline with non-Earth geometry to tighten the orbit before the Earth-Sun line swallowed it. Third, the blackout interval itself, roughly late October into early November, was expected on first principles. Solar conjunction is precisely the condition in which the sun sits near the target in our sky, wiping out contrast and limiting, safe pointing for many instruments. You don't need special pleading to explain the gap. You need celestial mechanics and caution. When the sun stands between us and the thing we care about, even deep space networks pause. Even rovers on Mars go quiet until the radio noise settles. The same story plays out for comets. If the elongation is too small, the sky says, wait. Notice what we are not claiming here. We are not stamping exact day-by-day invisible from all instruments dates for every telescope. Those schedules vary by facility and safety limits, and I cannot confirm a public, universal lockout list down to the day. What we can say and defend is the physical reason the window existed and why it straddled perihelion, the sun's proximity in angle, and the risk it poses to detectors and data quality. That's enough to understand the plot. The trial happened while the curtain was down. I cannot confirm specific daily access for each observatory. The conjunction rationale is the verifiable part. When the curtain lifted, the narrative changed register. The interstellar label didn't. The Hubble-era size constraints didn't. Our distance from the comet certainly didn't well be to 1.8 AU, about 270 million km on December 19, 2025. What shifted was the burden of proof. The geometry window ahead isn't a scare date. It's an observing opportunity, better signal to noise, broader longitude coverage, more spectra, and more chances to catch subtle non-gravitational tugs in the astrometry. That why we wait message is front and center in agency FAQs. Far, safe, scientifically useful. If part 1 was the first breath after the Sun 1 nucleus, no obvious multi-condensation chain, part 2 is the honesty about how we got there, through a gap we expected. Conjunction is not a conspiracy of silence. It's our field of view crossing a fire. We knew the test was running. We also knew better than to stare straight into it. The instruments closed their eyes. The physics didn't. When they open again, our job is to compare the before and after, like crime scene photographers. Same orbit family, hyperbolic. Same identity, interstellar, new heat history, and a body that, at first glance, still looks whole. Hold that thought for the next movement. A furnace nobody watched is still a furnace. If a nucleus can pass through and keep its outline, the next question isn't whether we missed the explosion. It's whether our rulebook for stress, venting, and interior structure is too simple. The blackout isn't an ending, it's a splice. We cut from prediction to retrieval what the light brings back, and what the numbers say it survived. Physics said it wouldn't survive. Perihelion is the audit no comet can skip. As a nucleus sweeps closest to the sun, the energy input spikes, surface temperatures rise fast, and volatiles race from solid to gas. Sublimation vents become jets. Jets become forces. Forces become torques. If the body is a porous rubble pile, rather than a single competent monolith, temperature gradients and asymmetric thrusts can pull at its seams until something gives spin-up, shelling, or outright breakup. This isn't mythology. It's how comets work when heat and momentum transfer crest together. Laboratory-anchored models and spacecraft data, especially from Rosetta at 67p, show that perihelion seasons can impart thermal stresses of many megapascals, comparable to or exceeding cometary tensile strengths, and that, outgassing, can measurably tug a nucleus off a purely Keplerian path while altering its spin state. Start with the heat. Near perihelion, the sunlit side cycles from cold to warm faster than the interior can respond. That mismatch stores stress. Models of cometary crusts tested against 1P, Halley, and generalized to other nuclei show perihelion thermal stresses reaching tens of MPa, easily above plausible tensile strengths for ice-dust mixtures. Fracture networks form, propagate, and open pathways for deeper volatiles to escape. On a weak, heterogeneous nucleus, that's the prologue to structural failure. On a stronger or more cohesive one, the same physics only reconfigures the vent map. Either way, the mechanical load is real. Now add momentum. Every molecule that leaves the surface pushes back. Where vents are unevenly distributed because of composition, illumination, or topography, the recoil is lopsided. That net thrust produces two things we can measure from Earth. Non-gravitational accelerations, small but cumulative in the orbit solutions, and changes in spin state precession, spin up, down, that can further stress a brittle body. Rosetta's long campaign at 67p is a template here. Teams quantified sublimation-driven forces and torques and linked them to water activity and regional venting patterns. Independent formulations parameterize how such forces perturb both the orbit and the rotation of irregular nuclei. Translated to plain speech, Perihelion is when the gas both moves the comet and tries to tear it apart. With 3I, Atlas, the conjunction blackout made the test happen behind a curtain, but the test was still the same. The deadly prediction was not superstition. It came from the cookbook above. If you assume a small, lightly bound nucleus with active vents, perihelion should be the place it fails. Because we didn't have a camera at the moment of maximum load, the honest way to talk about it is this. We can't certify exactly what happened at closest approach, but we can certify what should have been most dangerous and why many expected fragmentation signatures afterward. I cannot confirm a minute-by-minute outcome at perihelion. I can confirm the thermal stress and outgassing physics that make perihelion the crucible. This is also where morphology earns its keep. Entering solar proximity, you anticipate growing activity, jets that may swing with diurnal cycles, dust grains of different sizes peeling away into different tail components. Exiting, if a breakup occurred, you expect the classic fingerprints, multiple condensations inside a shared coma, string of pearls, chains, kinks, and subtails from newborn fragments. We have a live control in the same season, Comet C 2025K, 1 Atlas, unrelated to 3I but discovered by the same survey network, did fragment, with clear multi-blob imagery and reports across independent observatories. That is how a perihelion-stressed nucleus that fails announces itself. It may start with thermal fractures, but by the time it rounds the sun, the debris tells the story. 3I, Atlas, by contrast, came back into view with no publicly confirmed multi-nucleus chain. That doesn't prove the interior is pristine. Internal fragmentation is a serious, natural possibility, a way to enlarge the active surface area and intensify outgassing without an obvious exterior split. But the absence of the typical debris pattern shifts the immediate question from, did it explode, to, what combination of structure, composition, and geometry let it keep its outline? That's the productive question, and it's tightly framed by physics we can test. Stress fields versus strength, vent maps versus torques, grain size distributions versus tail geometry. I cannot confirm an internal fracture without higher resolution data. I can confirm that an internal fracture is a standard natural hypothesis when energy budgets look tight. Let's visualize the load. Picture a rotating, lumpy nucleus with a crust that's centimeters to meters thick over more porous interior ice. As the sun beats down, surface layers expand while shaded layers lag, cracks open. Gas pushes through the easiest paths, and the comet's irregular shape collimates some flows into jets. Where those jets are off-center, the reactive torque builds over hours and days, modulating spin and sometimes driving landslides or cliff failures. Rosetta imaged such changes in real time at 67p, and review studies link them to activity cycles and perihelion seasons. That is the baseline model that any mystery has to beat. If 3I, Atlas, behaves oddly, it must do so on top of this, not instead of it. There's a cautionary note to add. Thermal and mechanical fragility isn't a yes-no label. It's a spectrum set by microstructure, layering, volatile inventory, and illumination history. Recent work even explores how perihelion-induced stresses could initiate internal damage well before any visible split, with the eventual failure timed by spin state and geometry rather than a single temperature threshold. If you're looking for the number that predicts a comet's death, you won't find it. You'll find ranges, regimes, and tipping points, many of which perihelion sweeps past. All of this is why the "it" shouldn't have survived line was reasonable going in. It folds in heat flow, fracture mechanics, sublimation physics, and torque. It leans on spacecraft-era evidence, and it matches what we saw in a different comet this season that really did fragment. But shouldn't is not didn't. Nature has room for cohesion, for geometry that shares the load, for material properties that keep a shell intact while the interior rearranges itself. Our job after conjunction is to ask which levers 3I, Atlas, actually pulled. And that brings us to the contrast this section promised, entering versus exiting solar proximity. On the way in, we had projections, stress curves, expected jet evolution, risk factors. On the way out, we have constraints, no publicly confirmed debris chain, an OH-18cm detection that squarely supports ordinary cometary chemistry rather than transmitters, and a realistic observing plan keyed to distance and phase angle rather than drama. The next act is to test the powering question with numbers: how much water and which other volatiles, what tail grain sizes, what non-gravitational nudge in the orbit fit, so that whatever feels strange about 3I, Atlas, is either absorbed by the rulebook or flagged as where the rulebook bends. We can't replay perihelion, but we can read its fingerprints. Heat wrote in fractures, gas wrote in thrust. If a body as small as a few kilometers kept its silhouette, the message isn't magic. It's parameter space. Stronger patches, different layering, vent distributions that cancel rather than compound torque. There are many ways to just clear the bar. Our film will keep the tone we've set: calm, verifiable, and specific. The furnace was real. The prediction was logical. Survival is now a measurement problem, same trajectory, very different fate. If you want to see what real fragmentation looks like, don't look at 3I, Atlas, look at C, 2025, K1, Atlas. It's a different comet entirely. Same survey name, unrelated object. And in mid-November, it put on the textbook breakup. Multiple condensations inside one shared coma, irregular plumes, the telltale string of pearls morphology that only shows up when a nucleus actually comes apart. Gianluca Massi's Virtual Telescope project published a sequence of images on November. The thermal and mechanical hazards near the Sun are universal. Rapid heating builds stress across the crust. Sublimation vents impart thrust and torque. Weak interiors are tempted to unzip. When a nucleus loses that argument, you see K1S signature. Multiple bright knots sharing a common envelope. Uneven dust fans, subtails, and kinks spawned by newborn fragments. When a nucleus doesn't obviously lose, you don't see that signature. That doesn't certify the interior is pristine, but it does mean you haven't earned the word disintegrated. K1 earns it. 3I, Atlas, based on public evidence so far, doesn't. There's also a timing lesson. K1S breakup was not a single cinematic pop at perihelion. It was a process with a visible aftertaste. Observers reported a dramatic brightening and color change near perihelion green to more golden. Then the structure gave way later, under the compounded effects of heat history and asymmetric outgassing. By the time Massi's images crystallized the picture, the inner coma had become a miniature archipelago. That arc hint, stress, failure, is the one you'd expect from the perihelion rulebook. It's why, during 3I, Atlas's conjunction blackout, many prepared the same verdict in advance. The verdict simply didn't arrive. Visually, you can think of it as two model renders on the same screen. Left, a nucleus under heating load that fails crust fractures, vents migrate, the body sheds. You end up with 2 or 3 dominant fragments plus debris filigree. Right, a nucleus under similar load that keeps its silhouette still venting, still dusty, but presenting one central condensation when the glare lifts. K1 belongs to the left render, 3I, Atlas, so far to the right. The practical value of this side-by-side isn't drama, it's discipline. When viewers later ask, what would a real breakup have looked like? We can point to K1 and say, exactly that, and it keeps our language clean. Exploded isn't a vibe, it's an observation. If you can't circle distinct condensations in independent frames, you don't have a confirmed fragmentation. K1 clears that bar across multiple nights and sources. Articles from space.com and Live Science align with the virtual telescope sequence. Additional science pages and news desks picked it up as the comet approached its November 25 Earth flyby, still distant on astronomical scales. That Triangulation Observatory blog, plus specialist press, plus mainstream science media, shows you what consensus looks like when a comet breaks. This isn't to say K1 is simple. Breakups seed their own puzzles. How much mass did each daughter nucleus take? What's the grain size distribution in the debris? How did spin state evolve across the split? Did jets flip or merely remap? But those are post-breakup questions built on the foundation that the breakup is not in doubt. For 3I, Atlas, our questions are upstream: energy budget, vent distribution, and possible internal damage that increases the active area without an exterior split. 2 comets, 1 furnace, opposite outcomes, and that polarity is what makes the interstellar case compelling rather than confusing. So the narrative function of K1 in this film is simple. It's the control. It demonstrates, in the same observing season and news cycle, exactly how a sun-stressed comet announces failure to the camera. Well, carry that template forward as we review 3I Atlas's geometry problems, the anti-tail that isn't magic, and the chemistry that already has a firm anchor, the OH-DNCM line, water. With K1 as our benchmark for broken, we can keep our claims about 3I Atlas calibrated to what the data actually show. One frame resolved a question and birthed 7 more. After the conjunction, the first widely discussed post-sun frame did one blunt thing. It killed the certainly exploded headline. The morphology circulating on Nova 11 showed a single central condensation with a clean anti-solar tail, no publicly confirmed chain of daughter nuclei. What we can say with confidence is the baseline, 3I Atlas, is an interstellar comet on a hyperbolic path. NASA, with Hubble-era constraints placing the nucleus at roughly 0.445.6 kilometers. Those facts remain our reference frame as we look at any one image. 2 clarifications before we treat that frame as evidence. First, the pre-perihelion NOT campaign by David Jewett and Jane Liu is documented in a technical preprint using the 2.56M Nordic optical telescope, including activity, evolution, and dust behavior solid, citable work. Second, claims that the Nova 11 post-perihelion image itself came from Jewett and Liu on NOT are being propagated by commentary, for example. Medium posts, secondary news, rather than a primary release from the observers. I cannot confirm that provenance from a primary source yet. Treat it as reported rather than archived, while we wait for an official data page or paper. Even with that caution, one clean frame, whoever made it, still functions as a science prompt. Here are the 7 puzzles it writes on the board. 1. Why one nucleus? If the perihelion crush test had produced a classic breakup, we'd expect multiple condensations inside a shared coma. Our control this season, Comet C 2025K 1 Atlas, shows exactly that. Multi-blob images and day-to-day fragment motion, documented by the Virtual Telescope project and corroborated by Space.com. 3I Atlas, so far, does not show that signature in public material, so the external breakup case isn't earned yet. 2. Why the sunward structures? A tail that seems to point at the sun is not exotic propulsion. It's the anti-tail illusion, large, slow-responding dust in the orbital plane, plus the observer crossing that plane. This has been modelled since the 1972nd Sekanina et al. NASA. NTRS. So sunward by itself is not weird. The persistence and texture in 3I Atlas is the interesting part. 3. What powers the brightness and jets? The radio line detection of OH at 18 cm with Meerkat anchors the chemistry in ordinary comet physics. H2O broken by sunlight produces OH. This is not a transmitter. That single data point heavily weights natural outgassing as the driver behind the frame's clean tail. 4. Where's the energy budget tight? If a small nucleus appears highly active, either the active area is larger than we assume, for example, internal fracturing boosting vent count, or composition and grain physics are helping. That is a testable mismatch, not a reason to leap to engines. Spectra for H2O, CO, 2CO, and repeated OHX will tell us if sunlight can fully foot the bill. The image alone count. 5. What's the grain size distribution? The frame's geometry, tail width, curvature, depends on dust sizes and ejection speeds. Jewett and Luce, pre-perihelion NOT analysis, already argued for optically dominant 0.1 mm grains and sluggish response to radiation pressure, exactly the regime that breeds strong anti-tails under the right viewing angle. Does the post-sun morphology agree? We need consistent modelling runs tied to the new epoch. 6. Did the torque pattern change? A single image can't reveal spin state, but jets imply recoil forces. Over weeks, astrometry can expose non-gravitational accelerations. If the post-sun frame looks tidy, while the orbit fit shows fresh thrust terms that would steer us toward internal replumbing rather than exterior splitting. This is where December's geometry helps. beta S. N for position measurements at to 1.8 AU distance, about 270 million km, means tighter fits. It's an observing opportunity, not a hazard. 7. Who made that frame? Exactly, and with what setup? If it was not on NOV 11, the telescope is a 2.56 m facility at La Palma with a well-characterized imager, spectrograph suite for example, Olfos to 7.3 FOV, and high-quality optics. Documentation is public, but until the observers release a primary dataset or captioned figure, the correct way to reference the NOV 11 frame is reported and to cite the commentary source, not the scientists, for that specific post-perihelion claim. I cannot confirm a primary not archive for NOV 11 as of now. That's the honest way one frame earns its keep. For now, and replaces it with 7 quantitative questions we can actually answer. The rhythm from here is simple. Anchor to the facts that are already public and institutional, interstellar orbit, Hubble size bounds, O equals water, use the anti-tail literature to separate geometry from mystery, and let new spectra and astrometry decide whether the energy budget really strains the natural comet playbook or merely stretches it. No coma fragments, no trailing fields, just one. When you study breakups long enough, your eyes learn the tells. True fragmentation advertises itself. Multiple bright condensations sharing a single diffuse envelope, string of pearls, knots drifting apart night by night, fans and kinks that don't belong to one body anymore. Those aren't vibes, they're diagnostics established across classic split comet literature and spacecraft-era imaging. If you can circle distinct condensations in independent frames, the nucleus has failed. If you can't, you haven't earned the word disintegrated. This observing season handed us a control group on a silver platter. C. 2025. K1 Atlas, not the interstellar comet. Just a survey namesake came out of its October 8 perihelion and then visibly fell apart. The Virtual Telescope project stitched night-to-night sequences showing several subnuclei in a common coma, while Space.com and other outlets ran the same story. By November 11/14, K1 was a miniature archipelago, its debris plume trailing the lead fragment. That's what a breakup looks like in public data. Repeatable, multi-source, multi-blob. Now put 3i, Atlas, next to that template and look for what's missing. In the first post-conjunction views, there wasn't a chain of daughter nuclei you could count. There wasn't a beaded spine through the inner coma. The antisolar tail was clean rather than littered with bright clumps. As of the latest public summaries, agencies still frame 3i, Atlas, as an interstellar comet on a hyperbolic path with a single central condensation. No official multi-condensation fragment train has been confirmed. That distinction matters. K1 crosses the morphological threshold. 3i, Atlas, so far, does not. Non-fragmentation also has positive signatures. Isophotes, contours of equal brightness, around a single central peak fall off smoothly. Jets appear as sectorial enhancements, but converge back to one photometric core. The ion tail stays narrow and antisolar, while any sunward features resolve to antitail geometry, large grains in the orbital plane, seen edge-on rather than to newborn shards. This geometry has been modelled for decades. A sunward-looking structure is not exotic propulsion, it's dust physics plus viewpoint. In a one-nucleus scene, those lines add up to determination, not debris. To be clear about what we can and cannot claim, a single, tidy condensation doesn't prove the interior is pristine. Internal cracking can multiply vents without an external split. That's a standard, natural hypothesis when activity looks strong. But the camera's test for external breakup is stubbornly simple. Do we see multiple condensations in a shared coma, in independent images, across multiple nights? With K1, yes. With 3i Atlas, not in the public record so far. The burden of proof stays on any claim of disintegration until those pixels exist. If you need one more reason to be disciplined, rewind to Shoemaker, Levy 9, the case for learning what fragmentation must look like. It's a string of beads train set, the taxonomy many of us still use. Discrete nuclei, debris clouds in tow, dynamics you can measure rather than imagine. Ever since, the field's language has been careful. Fragments are counted, separations are tracked, Brightness profiles separate jets from shards. We owe that rigor to every new comet that rounds the sun and comes back looking deceptively orderly. So our visual cue for this section is a split screen that trains the audience's eye. Left, a pre-post pair for C, 2025K. 1, the before with a single core, the after with a broken nucleus and lumpy inner coma. Right, the equivalent for 3I, Atlas before with active jets and occasional sunward geometry. After, with one central condensation and a clean anti-solar tail. The point isn't to declare mysteries solved, it's to calibrate expectations. When we say no debris, we mean no confirmed multi-nucleus morphology. When we say determination, we mean the silhouette stayed whole at the scales our images can see. Hold on to that trained eye as we move forward. The next acts won't lean on single pictures. They'll stack chemistry. O at 18 centimeters equals water outgassing. And dynamics, non-gravitational nudges, grain size modeling, on top of what the shapes already told us. If something about 3I, Atlas, truly breaks the rulebook, it will have to pass the same tests K1 just did, in reverse. It will have to show it. If it's broken, why is it still firing? Post-sun, 3I, Atlas didn't return as a sleepy ember. It came back active, a single central condensation with a clean anti-solar tail and, at times, sunward-facing structure that makes non-specialists think thruster. In comet physics, that shape has a name and a file cabinet: anti-tail. Large, sluggish dust grains populate the orbital plane. When our viewpoint crosses that plane, geometry stacks their light into a sunward spike. This has been formalized since the 1970 seconds and does not require exotic propulsion. The more important line is the radio one. O, at 18 centimeters. South Africa's Meerkat array detected hydroxyl at 1,665, 1,667 megahertzes, a classic water proxy formed when sunlight breaks H2O. That's textbook outgassing, not a transmitter. A single robust detection doesn't answer every puzzle, but it nails the headline. The object is still venting volatiles after perihelion. Natural comet chemistry remains the best fit explanation for what we're seeing in the sky. Before conjunction, David Jewett and Jane Lewis' Nordic Optical Telescope campaign had already traced an activity evolution. Early season sun-facing fan, later, a dominant anti-solar tail behavior they tie to large, 0.1 m, dust and slow ejection speeds, to 5 meters per second. Those parameters make anti-tails likely whenever geometry cooperates, and also imply substantial momentum carried by grains that don't quickly blow away. In plain language, a comet like this can keep looking busy even as the viewing angle flips across perihelion. How many jets? From public data alone, we can't responsibly number them post-perihelion. What we can say is what the morphology and radio tell us together. There are active vents somewhere on the surface, or just beneath a fractured shell. They're pushing material out, and the recoil forces add up over time into the small, measurable non-gravitational accelerations that orbit fitters look for. That's the same physics Rosetta used to connect vent maps to forces at Comet 67P. For 3I, Atlas, December's improved geometry will simply make those fits tighter. I cannot confirm a post-perihelion multi-jet count. I can confirm ongoing outgassing supported by OH and shape. The sunward features deserve a final, calm word. If the nucleus had actually shed a string of daughter bodies, the inner coma would look lumpy, multiple condensations, beaded structure, uneven fans, exactly what we do see in C, 2025 K1, Atlas, after its breakup. In 3I, Atlas, the post-sun images discussed publicly show one core with structured dust and an anti-solar tail. That makes the anti-tail explanation big grains plus plane crossing the discipline choice, not a hand wave. So yes, still jetting. And no, not wrong at all once you put the right physics under it. Water chemistry on the radio, large grain dust dynamics in the images, activity that remained through the furnace. If the interior is fractured, that only increases the active area without demanding visible shards. One natural way to square strong activity with a single central condensation. The next tests are specific. Repeat, O, get H2O, CO2, CO spectra. Watch astrometry for fresh non-grav terms. Those numbers will tell us whether the powering budget really strains sunlight, or whether sunlight, dust, and geometry, together, already explain the show. Why is a tail pointing at the sun? Because our eyes are easy to fool, and dust is patient. A sunward tail isn't a thruster or a rule broken. It's a projection trick with heavyweight grains. Large particles sub-millimeter to millimeter and up don't yield quickly to radiation pressure. They linger in and near the comet's orbital plane, moving almost ballistically after launch. When our line of sight crosses that plane, those grains stack into a narrow spike that seems to aim at the Sunday. It's called an antitail, and it's been modelled for decades. The scaffolding is the Finson-Probstein dust tail model. Draw synchrones, same release time, and syndines, same radiation pressure parameter, beta, a proxy for grain size, and you can map where different dust populations should appear for any viewing geometry. The surprise is how well this simple framework explains counterintuitive shapes, especially when big grains, small beta, dominate the optics. Under the right angle, synchrones, syndines bunch into a sunward spike without any exotic physics. Sekanina and colleagues turned that scaffold into a playbook for anti-tails, predictability from geometry, plus a reservoir of large grains ejected near perihelion. When the Earth-Comet-Sun configuration goes edge-on to the orbital plane, the big grains form a thin neckline sheet that projects as a sunward feature. Kohutek's famous spike in the 1,970 seconds was explained exactly this way. Particle flow phenomenon, not propulsion. The same logic is what disciplines our reading of 3I, atlas images that show persistent sunward structure. How big is big? Classic thermal, infrared arguments constrained anti-tail grains to tens of microns, up to millimeters, and potentially larger aggregates, to resist radiation pressure long enough to build a coherent sheet. Rosetta later gave us ground truth at 67p. Two dominant dust families compact, 0.031 mm, and fluffy 0.2, 2.5 mm aggregates, demonstrating that millimeter-scale material is not exotic at all. If 3I, Atlas, is feeding a similar size distribution, a sunward spike becomes an expectation under the right viewing angle. Now, picture the impossible in vectors, not vibes. In a 3D map centered on the nucleus, draw 1. The sun vector radiation, solar wind line. 2. The comet's velocity vector in its orbital plane. And 3. Our line of sight. Small, bright ions. Beta, effectively large, stream, antisolar, your classic gas, ion tail. Larger dust grains launch near the surface normal of active vents, then settle toward or remain near the orbital plane as radiation pressure under-accelerates them. When our viewpoint skims that plane, the projected column density along our sightline spikes sunward, even though each particle's actual motion is not toward the Sunday. The tail is a perspective-dense sheet, not a thrust plume. Two tests keep this honest. First, time. Antitails are geometry-tied. They strengthen and fade as the observing angle changes. As Earth moves off the plane, the sunward spike should weaken or morph predictably under Finson-Probstein fits. Second, grain physics. Spectral color, polarization, and surface brightness profiles constrain grain sizes and production epochs. A dominance of large, slowly accelerated grains should be consistent across these diagnostics. Both tests are routine in comet work, and both can be applied to 3I Atlas with the December geometry window, beta S/N, broader longitudinal coverage. A common misunderstanding is to treat any sunward feature as evidence of controlled jets or navigation. Real jets exist. Of course, they're how dust gets into space, but their recoil forces show up as non-gravitational terms in orbital fits and as spin state changes, not as a static sunward spike. Whipple's classic analysis linked net jet thrust to small orbital deviations. Rosetta mapped vent geometry to forces and torques at 67p. Those are dynamical fingerprints we can measure. A perspective anti-tail, by contrast, is a morphology fingerprint we can predict from geometry and grain size. Different draws, different evidence. So the impossible resolves to a checklist we can show on screen. Geometry, Earth crossing, or skimming, The comet's orbital plane projections spike sunward. Grains, large tens of mu, m to m, dust, persist near the plane, building a thin sheet, neckline, model. Vinson-Probstein synchrones, syndynes reproduce the spike without invoking propulsion. Dynamics crosscheck. If jets were thrusters, we'd expect distinctive non-grav terms. Spin behavior incompatible with a passive sheet alone. We can and will look. That's how we turn a crowd-pleasing optical illusion into a testable scene. Our visual cue for this chapter is a clean 3D vector render. Sun vector, orbital plane, Earth line of sight, plus an overlaid synchrone, syndyne grid, showing why a sunward spike appears exactly when it should. We'll let the camera glide from the 3D model to real frames of 3i, Atlas, where the spike lives and fades on schedule. If it keeps the schedule, it's geometry. If it doesn't, that's when the mystery starts earning its name. The comet's mass doesn't match its actions. If you take the most cautious, agency-vetted number we have for 3i, Atlas, the Hubble upper bound of, to 5.6 kilometers for the nucleus diameter, and ask it to power everything we've seen, the ledger creaks. A few hundred meters to a few kilometers across is what NASA gives us today. Hyperbolic, interstellar, small. That's our baseline before any mystery is added. Now look at the bill some analyses present. Harvard astrophysicist Avi Loeb has argued in public notes that the apparent activity could imply mass loss on the order of billions of tons across the month around perihelion, and an energy uptake of roughly 3 times 10, 18 joules, numbers that, if taken at face value, feel like a 23 km class energy output, rather than A is less than or equal to 5.6 km body. He frames this as an energy budget paradox. The tank seems too small for the thrust we think we see. These figures are not a community consensus. They are a provocative calculation that invites measurement. What would have to be true for the paradox to be real? First, our size bound is near the low end, so the tank is small. Second, that the gas, dust, production rates inferred from brightness and morphology are truly that high. Third, that the active area is not larger than we think, that is to say, no hidden interior fracturing that multiplies vents without obvious exterior splitting. Each of those premises has levers we can test with spectra, polarimetry, and refined astrometry. Until then, the comet's mass doesn't match. Its actions is a question, not a verdict. There's a cleaner anchor while we argue. Chemistry. South Africa's Meerkat array detected the 18 cm hydroxyl OH lines 1,665, 1,667 MHz from 3i Atlas classic water photolysis, the radio fingerprint of ordinary cometary outgassing. That doesn't settle rates, but it nails the mechanism. Sunlight in, H2O out, OH in the radio. Whatever the energy budget is, it starts with a natural tank and a natural pump. So how could a small tank look like a big engine without breaking physics? Hidden active area. Internal cracking increases surface area behind a mostly intact shell, bigger radiator, same silhouette. Natural, testable, with line ratios and thermal modeling. Absence of multi-nucleus debris in public imagery argues against an external split, not against internal damage. Composition leverage. If CO2-CO fractions are higher than naive guesses, you get more bang per square meter at a given heliocentric distance. IR spectra, we'll say. Grain economics. Large, slowly accelerated dust, anti-tail regime, carries momentum and optical brightness efficiently. The visuals can exaggerate apparent power relative to H2O alone. The anti-tail literature predicts this geometry without engines. Inference bias. Converting brightness and shape into production rates is model-dependent grain size distribution. Albedo, phase law. Small shifts there can compress or inflate the tons per month headline by orders of magnitude. Vinson-Probstein and its descendants are first-order tools, not oracles. If you want a picture to carry into the voiceover booth, use the fuel tank analogy. Imagine our nucleus as a golf ball of ice rock compared to a semi-truck tank. You'd think you need to feed that much plume. The paradox claim says, I see a semi-truck plume from a golf ball tank. The natural comet reply is, Check the plumbing and the nozzle math before you order a new truck. The plumbing is internal fracturing. The nozzles are vent maps and grain sizes. The plume brightness is a function of geometry as much as gas. We will literally visualize this with a tank versus output gauge on screen. Analogy. Numbers per cited sources above. There is a hard number test coming. If the budget is really off, it should announce itself in 3 places at once. 1. Line rates. H2O, CO2. CO production from spectra should sum to a solar-powered ledger that either balances or doesn't. If it doesn't, show by how much and when. 2. Dynamics. Orbit fits should pick up non-gravitational accelerations consistent with the inferred mass loss. If the push is that large, the math must close in the trajectory. 3. Thermal inertia. Mid-IR constraints on surface temperature and beaming should agree with the claimed active area. Otherwise, the radiator is smaller than the invoices. Each of those can be pursued in the favorable mid-December geometry. Earth comet is approximately equal to 1.8 AU, beta S, n across longitudes. A point agency FAQs and coverage keep emphasizing as an observing opportunity, not a hazard. There's a cultural duty here, too. High-profile voices can accelerate curiosity, and that's valuable, but our script owes the audience a ladder they can climb. Rungs 1 through 3 are institutional. Interstellar orbit and size bounds. NASA, Hubble, Oh-Hate radio detection, Meerkat, reported by mainstream science outlets, and a control comet that really did fragment this season. C, 2025K, one with multi-blob imagery. Only after those rungs do we introduce the paradox math with a label. 1. Researcher's calculation. Intriguing, awaiting measurements. So we keep the line for pacing. The comet's mass doesn't match its actions, but we deliver it as a challenge to be tested, not a conclusion to be worshipped. If the golf ball truly behaves like a semi-truck, the spectra and the orbit will prove it. If not, sunlight plus fractured plumbing and big grains will keep the story comfortably inside the rulebook. Strange looking, sure, but not strange powered. It's accelerating but not breaking apart. Non-gravitational forces are not sci-fi, they're comet physics. When sunlight drives gas out of vents, the recoil nudges the nucleus and over weeks measurably warps the best fit orbit. This is the rocket effect behind classic comet models, Whipple-Marsden parameters, and was quantified in detail at 67p by Rosetta. Outgassing produced both accelerations and torques without any engines involved. That's the frame for 3i Atlas. You can have thrust without a breakup. If vents keep firing while the body stays in one piece, you expect a small but real deviation from a purely gravitational trajectory and possibly a changing spin state consequences. We can test with precise astrometry and light curve work as geometry improves in December. This is standard practice. Many comets show such terms in their orbit solutions. Where the debate heats up is how much thrust the pictures imply. Avi Loeb has posted a series of blog essays arguing that the observed jets, anti-tail, imply an unusually large mass loss rate. He sketches numbers up to 50 billion tons per month, and therefore a large rocket effect. From momentum conservation, he relates mass fraction loss to the non-gravitational acceleration and an assumed gas speed, and in some write-ups infers tens of % mass loss during the perihelion interval under his adopted parameters. These are public personal calculations, not a community consensus. Two things can be true at once. 1. O, at 18 centimeters, was robustly detected with Meerkat, which anchors ordinary water-driven outgassing. 2. The exact magnitude of the mass loss, and thus the rocket thrust term, is still an open measurement problem. Mainstream coverage has emphasized the first point and urged caution about extraordinary interpretations attached to the second. How do we adjudicate too much thrust versus just enough? Astrometric fit. If the orbit requires a significant non-gravitational term, it will drop out of the residuals. That term can be compared to physically plausible production rates and gas speeds. Rosetta-era studies show this comparison is routine and self-consistent for comets. Line rates, spectroscopy, H2O, CO2, and repeated OH measurements should converge on mass loss numbers. If those fall orders of magnitude below what a claimed thrust would require, the claim weakens. If they agree, it strengthens. Spin torque. Strong, asymmetric outgassing should also torque the body. Rosetta connected vent maps to torques at 67p. A large rocket term with no compatible spin behavior would be suspicious. A subtlety about the images. Anti-tails and broad fans can exaggerate power to the eye because large grains, low beta, dominate the brightness, yet don't contribute much to gas rocket thrust. Finson-Probstein modeling, plus grain size constraints, color, polarization, IR, are needed to convert looks strong into is strong. That modeling can easily move mass loss inferences by orders of magnitude. What about the headline claim, it's accelerating but not breaking apart? That's entirely compatible with a natural comet. Kinetic recoil from venting can be present whether the shell looks tidy or not. C. 2025. K1. Atlas shows the opposite case, clear fragmentation, while 3I. Atlas shows a single condensation in public summaries so far. One proves that breakups shout in pixels. The other keeps the door open for intact shell thrust. Bottom line for the script, and for viewers who want receipts. Established physics. Outgassing measurable non-gravitational accelerations. Torques, verified at 67p. Standard in orbit fitting. Established data for 3. I divided by Atlas, 018 centimeters. Detection equals water chemistry. No publicly confirmed multi-nucleus chain post-Sunday. Active claims, under review. Blog-level calculations proposing very large thrust, mass loss up to tens of %, based on image-inferred areas and assumed speeds. These await independent spectra plus astrometry. Context from experts. Science outlets and researchers have cautioned against leaping from anomalies to propulsion, alien narratives. They point back to natural comet mechanisms pending measurements. So yes, the comet can accelerate without shattering. The open question is how much. December's geometry is where that number gets real. If the required non-grav term is big, the spectra and orbit will agree. If it's modest, sunlight plus vents will close the ledger quietly. Either way, the test is in the math, not the hype. It wasn't a signal, but it said something. The first firm voice we heard from 3I. Atlas, after the furnace wasn't a ping, a beacon, or a whisper from machines. It was chemistry. South Africa's Meerkat array detected hydroxyl at 1,665, 1,667 MHz, the classic 18 cm OAE lines that appear when sunlight breaks water apart in a comet's coma. That single result anchors the entire narrative. A natural engine, solar-powered, venting volatiles. Not aliens, not propulsion, photolysis and outgassing, exactly where they should be. If you've never lived in radio, here is what that means. Cometary water, H2O, doesn't usually shout directly on the radio. Its fragment O does. UV sunlight cracks H2O, OH plus H, and those OH radicals imprint narrow spectral lines near 18 centimeters. Radio astronomers have used these lines for decades to track gas kinematics and estimate water production rates. The backbone of is it active and how much? Diagnostics for comets. 3I. Atlas. Joining that club is exactly the opposite of exotic. It's a textbook signature checked off in the interstellar context. Clarity matters because rumor thrives in static. Headlines frame the detection cleanly. First radio waves from 3I, Atlas, and not aliens. The phrasing is more than PR. It's a caution label for the public. A narrow molecular line, centered where chemistry says it should be, is not a modulated transmission. It's a thermometer and a flow meter, telling us that water is present and being processed by sunlight. That's the kind of result that collapses many dramatic branches of the decision tree at once. Put it next to the geometry we already tamed. A sunward spike in images, the anti-tail dropped into the dust plus viewing angle draw. The OH line drops into the gas plus sunlight draw. Two illusions, one visual, one cultural, dispelled by two ordinary pieces of comet physics. The remaining puzzles, energy budget, active area, grain sizes, non-gravitational tugs, are real, but they now sit inside a natural framework rather than outside it. Institutional context backs the frame. NASA. ESA's Hubble summary still constrains the nucleus to an upper limit diameter of to 5.6 kilometers, possibly much smaller, on a hyperbolic interstellar trajectory facts the audience can verify without wading into commentary. The OH detection complements that, a small, fast visitor that behaves like a comet at the molecule-by-molecule level. That pairing size, trajectory from Hubble, chemistry from radio is why this section's tone is calm. So what did the line actually say? That water is being released and processed, that the coma is alive, and that any thrust we infer starts with sublimation, not engines. It also sets up the next measurements. Repeat O to watch variability. Secure IR spectra for H2O, CO2, CO to budget the volatiles. Compare those line-based production rates against the non-gravitational term in the orbit fit. If the math closes, too much thrust fades into parameter choices. If it doesn't, well, know exactly where the shortfall lives line by line, not headline by headline. That's the grounding clarity the audience deserves. The comet spoke, and it spoke chemistry. Well, keep breathing at that cadence, light, silence, memory, breath, because the numbers now match the mood. Light returned after conjunction. Silence became a datum. Memory logs a clean O8 detection. And breath slows the film to let ordinary physics do the heavy lifting while we measure the rest. What if it broke inside, but stayed whole outside? There's a version of this story that doesn't need engines or miracles. The nucleus takes the sun's punch, the shell holds, and the inside rearranges. In comet science, that picture has a name: a rubble pile nucleus, low density, high porosity, weak tensile strength, layers, and voids inherited from early aggregation and later processing. Rosetta's long campaign at 67P cemented this baseline. Comet nuclei are fragile, cluster-like bodies with very modest strengths and complex internal structure. That's not a rumor. That's the reference model modern work starts from. If a nucleus like that suffers thermal stress around perihelion, cracks propagate inward before they ever advertise themselves outside. Modeling and spacecraft-era analyses show perihelion seasons can generate stresses comparable to or exceeding expected strengths for ice dust mixtures. Recent literature keeps revisiting the same theme: low strength, loosely bound matrices are prone to stress-initiated damage without an immediate surface rupture. In plain English, heat can shuffle the plumbing before it shatters the walls. Why this matters for 3I? Atlas is the active area problem. If the interior fractures, it can multiply vent pathways behind a mostly intact shell. More vents mean more gas. More gas means more recoil, and more dust entrained. Yet a camera at post-sun geometry would still record a single central condensation. No multi-nucleus chain. That's a natural way to square strong, continuing activity with a silhouette that looks whole. It also lives comfortably alongside the radiochemistry. The 18 cm OH line hydroxyl from sunlight cracking. H2O anchors the outgassing mechanism to ordinary water, not transmitters. Let's separate what we know from what we're testing. Known. External. No publicly confirmed post-conjunction multi-nucleus morphology for 3I, Atlas so far. The object presents one central condensation in widely discussed frames. Therefore, no earned claim of an external disintegration. Known, chemical. O at 1,665, 1,667 MHz detected textbook cometary water proxy. That's outgassing speaking in radio, not a signal. Plausible, internal. Perihelion stresses plus weak, porous structure, internal cracking, larger effective active area without an exterior split. This mechanism is standard in comet literature and consistent with Rosetta-era nucleus properties. Where's the proof line? We don't have direct evidence of internal fragmentation in 3I, Atlas. I cannot confirm that. What we can do, starting in the better December geometry, is mount tests that would favor or disfavor the hidden fracture picture. 1. Production rates that rise without shards. If H2O-CO2-CO line fluxes imply a larger active area than a smooth shell would allow, yet images remain one core. Internal plumbing becomes the economical explanation. Repeat O. Add IR spectroscopy. 2. Non-gravitational terms that fit the gas. Orbit solutions should show recoil consistent with measured production rates and gas speeds. Yeoman's Marsden-style parameters let us check the math against sublimation physics. 3. Spin state behavior without exterior splits. Strong, asymmetric venting torques a nucleus. Rosetta-linked vent maps to torques at 67p. A similar torque signature in 3i. Atlas absent debris would point to interior replumbing over exterior failure. A quick caution about Look's powerful images. Brightness and tail texture can be dominated by large grains that carry momentum differently than gas and linger near the orbital plane. If grain physics is doing heavy lifting, visuals can oversell the demanded gas budget. That's why geometry, dust modeling, and line-based production rates have to meet in the middle, not in a headline. So we hold the hypothesis where it belongs. Speculative but plausible, grounded in weak strength, rubble pile nuclei and perihelion stress mechanics, and now constrained by a real chemical detection, oh hey, that locks the engine to sunlight. If December's spectra and astrometry say the active area and recoil are large, while the outline stays single-core, interior damage becomes the boring, beautiful answer. If instead the numbers are modest, we won't need hidden fractures at all, just sunlight, vents, and dust doing what they've always done. Jetting against physics. Still going, if you stitch the season together, the line is unbroken. In July, 3i, Atlas, showed a sun-facing dust fan. By September, it was dominated by an anti-solar tail, exactly the transition David Jewett and Jane Liu documented from Nordic optical telescope data, explained by large, slow dust that responds sluggishly to radiation pressure. In plain terms, sustained activity, changing its look as geometry and grains changed, not a switch that flicked off. Across perihelion, the engine didn't die. The radio heard it. South Africa's Meerkat array detected the 18 cm OH lines, 1,665, 1,667 MHz, the textbook water proxy created when sunlight photolyzes H2O in a cometary coma. Headlines framed it clearly. First radio from 3i, Atlas, and not aliens, because narrow molecular lines at those frequencies are chemistry, not transmissions. Whatever the interior did or didn't do, outgassing persisted through the furnace. That persistence makes the sunward features after conjunction easier to read. A spike aiming at the sun looks like a violation. The literature calls it an anti-tail large grains lingering near the orbital plane, projecting as a sunward sheet when our viewpoint skims that plane. Sekanina's classic analyses and later reviews turned this from oddity into routine. Geometry plus big grains, not thrusters. The same dust regime proposed by Jewett and Liu, 0. 1 im, ejection, 5 meters per second, is exactly the regime that breeds strong anti-tails when the viewing angle cooperates. What about how many jets? From the public record, I cannot confirm a specific post-perihelion 7+ jet sources count. That level of detail needs resolved imaging, photometry, and consistent modeling tied to dates and phase angles. What is supported? 1. A pre-perihelion evolution consistent with active venting and large grains. 2. A perihelion-era OH detection that anchors ongoing water outgassing. And 3. Post-sun morphology compatible with anti-tail geometry rather than debris. Those three together justify the on-screen claim that the comet kept firing without claiming a numbered jet map we don't yet have. For the film language, keep the persistent tactile. Early season frames, a bright, sunward fan that reads as push. Late September, the anti-solar tail takes over same engine, different projection. October 24. Oh, in the radio, a molecular metronome that says water is still leaving. Mid-November. After conjunction, a single central condensation with structured dust and a clean anti-solar tail, plus intervals where the anti-tail reappears exactly when geometry should allow it. That's a continuous respiratory trace, not a flat line. Why this matters for the powering chapter ahead. Persistence trims the hypothesis tree. If activity had collapsed after perihelion, we'd chase explanations for a spent tank. Instead, the through line favors natural continuity, sunlight, vents, large grains, while leaving room for interior changes, hidden fracturing that enlarges active area to explain any energy budget tension. The job for December's window is to quantify the persistence, water, CO, 2, CO line rates, polarization, color for grain sizes, and orbit fits for non-gravitational terms. If the numbers cohere, Still jetting will move from montage to math. Hess controversial, but the math is clean. Every good mystery invites a counter-narrator, someone who takes the same frames and tells a different story with equations. For 3i, Atlas, that voice has been Avi Loeb. In a steady stream of public posts, he argues that the comet's apparent activity implies a mass-force mismatch, jets too extended, thrust too large, and a mass loss that may reach billions of tons per month, all difficult, he suggests, to reconcile with a nucleus bounded by Hubble at is less than or equal to 5.6 kilometers. He lists anomalies, from jet orientation to anti-tail structure, and keeps a provocative conclusion on the table. Natural is possible, but artificial cannot be excluded. This film owes him a fair hearing and a careful line. First, what his posts are, and aren't. They're personal essays and calculations published on Medium, not peer-reviewed papers, not institutional statements from Harvard or NASA. They raise testable claims and propose eye-catching inferences. They are not the community consensus, nor the official positions of his university. We cite them as one researcher's public analysis to be weighed against measurements. Second, what do the numbers we have already say? NASA's public brief places 3i, Atlas, on a hyperbolic trajectory with a nucleus no larger than about 5.6 kilometers across, and potentially much smaller constraints from Hubble imaging that define the fuel tank before any outgassing arithmetic begins. That size frame is institutional, archived, and verifiable. Third, what the radio said clearly. South Africa's Meerkat detected narrow OH lines at 1,665, 1,667 megahertzes, the classic 18 cm signature of water, photolysis in cometary comet. Mainstream coverage emphasized the key point. This is chemistry, not a modulated transmission, and it anchors the engine to sunlight and ice. Whatever else we debate, O8 is the comet speaking water, not message. Now the tension. Loeb's thrust narrative hinges on converting morphology into momentum. Take bright, extended jets and anti-tail structure and infer large mass loss rates and high exhaust speeds. Then, from momentum conservation, conclude a big non-gravitational push, possibly demanding a much larger body or thrusters. The counter from many comet specialists runs through two cabinets marked geometry and grains. Anti-tails are a perspective effect of large, slow-responding dust in the orbital plane, Vinson-Probstein synchrones, syndines, and brightness can be dominated by big grains that carry optical weight without implying extreme gas speeds. In short, visuals can oversell power unless they're tied to grain physics and viewing angle. That objection isn't rhetorical. It's published context. Classic analyses of anti-tails, Sekanina and contemporaries, explain sunward spikes with millimeter-scale dust sheets and plane-crossing geometry, no propulsion required. Recent explainers aimed at the public, written by astronomers and science outlets, reiterate the same. 3i Atlas looks unusual, but unusual sits comfortably inside comet physics, unless spectra and astrometry say otherwise. There's also a quality control loop in the community. Detailed rebuttals by researchers, for example, Jason Wright, have catalogued where they think Loeb's anomalies reflect model choices, misread geometry, or selective priors, rather than data that actually break the rulebook. Those critiques aren't verdicts, but they're the kind of friction that keeps extraordinary claims from skating past ordinary checks. So how do we keep the tone measured while honouring the challenge? We put both stories on the same scoreboard. Size, frame, tank. Hubble upper bound, 5.6 kilometers, hyperbolic, interstellar. If later imaging moves this, we move with it until then. It's our baseline. Engine ID chemistry. O at 18 centimeters detected by Meerkat water outgassing, not transmitters. This sets the mechanism and calibrates line rate expectations. Morphology. Shape. Anti-tail and long jets must first pass the geometry. Grain test. Vinson, Probstein, and Sekanina-style modelling can reproduce sunward spikes without engines. Dynamics. If the rocket effect is as large as claimed, it must appear as a significant non-gravitational term in the orbit fit and, ideally, compatible spin-torque signatures, Rosetta-era crosschecks. This is where December's geometry helps most. On the public communication side, there's consensus about one thing: avoid letting maybe metastasize into is. Live Sciences reporting, along with other outlets, has repeatedly underlined that 3I, Atlas, remains consistent with a natural comet and that spectacular rumors, explosions, spacecraft haven't passed the measurement bar. That isn't a dismissal of curiosity. It's a prioritization of receipts. Where does that leave our film's narrative voice? Exactly where it belongs. Appreciative of a noisy challenger, anchored to quiet numbers. We let Loeb's posts sharpen the questions. How big is the non-grav term? How fast are the gases? How large is the active area? Then we answer those questions with the only tiebreakers that matter: spectra and astrometry. If the mass, force ledger really can't balance for A is less than or equal to 5, 6 km tank under solar power, the discrepancies will stack across independent instruments. If it can balance because of internal fracturing, bigger, effective, active area, composition, and grain economics, then controversial becomes a footnote under measured. The motif returns as our metronome: light, silence, memory, breath. Light gives us OH and shapes. Silence is where we refuse to upgrade speculation to fact. Memory holds the Hubble bounds and the classic dust models. Breath slows the cut to December. When geometry turns debate into datasets, he speaks. The numbers do, too. Well, let the microphone favor the one that doesn't need adjectives. December 19 is not far away. Circle the date because geometry is about to do us a favor. On the 19th of December 2025, 3I, Atlas, makes its closest approach to Earth, about 270 million km, roughly 1.8 AU. That distance isn't close for drama, but it is ideal for clean measurements across longitudes and instruments. Steadier astrometry, better S, N, and coordinated spectra that can finally balance the energy ledger. 3 pillars will shape the window: Hubble imaging, morphology, constraints. Hubble already gave us the size frame: a nucleus no larger than to 5.6 kilometers, and possibly much smaller. Around closest approach, HST can refine morphology: central condensation versus any faint companions, jet fans versus debris texture, and bracket the coma's brightness profile with consistent filters. This keeps the did it fragment question honest while anchoring model inputs for dust production. JWST composition. The budget in molecules. JWST has the right tools for volatile accounting. NIRSPEC and MIRI can separate H2O, CO2, CO, and trace organics, ICES, the very species that decide whether sunlight alone can power the show. We already have interstellar context proof that Webb can do this. A published NIRSPEC campaign found 3I, Atlas's coma, to be CO2, dominated with H, 2O, CO, OCO, OCS, a sulfur-bearing molecule, water ice, and dust also present one of the highest CO2, H2O ratios recorded in a comet. The operational guardrails matter too. JWST can only observe targets within a solar elongation of to 85 degrees, 135 degrees. But during the December window, that field of regard allows practical scheduling for moving targets. Translation, chemistry, on demand. Rubin Observatory Cadence, alerts, context. Rubin's survey mode isn't a spectrograph, it's a metronome. Its prompt pipelines and solar system processing turn night-by-night imaging into fast alerts and day-scale catalogues for moving objects. Even if 3I, Atlas itself is faint for small aperture photometry, Rubin's cadence and alert ecosystem help pin motion, catch subtle morphology changes, and synchronize follow-ups, HST, JWST, ground IR, across the community. It's the when to look machine that your precision instruments listen to. What, specifically, are we trying to read out of the sky? Volatile ratios that settle the bill. JWST spectra will quantify H2O, CO2CO, and species like OCS, testing whether a CO2-rich coma can explain the apparent big engine from a small tank without exotic assumptions. These line rates, compared against brightness and dust models, turn looks powerful into is or isn't powerful. Astrometry that hears the rocket effect. High-precision positions across the window will reveal non-gravitational terms in the orbit fit. If thrust is large, the residuals won't hide it. If modest, the ledger will close quietly under standard sublimation physics. Morphology that refuses hype. Hubble-class imaging at improved phase angles can confirm a single central condensation or not, and map jet sectors cleanly. With C, 2025 K1 as our in-season control for what real fragmentation looks like, this keeps our language disciplined. Set expectations, not rumours. The OH line that Meerkat caught at 18 centimetres already told us the engine is water chemistry, not transmitters. December is where we quantify how much water, and CO, 2CO, and whether the dynamics match. Think of it as a three-lock safe. 1. Spectra production rates. 2. Astrometry, recoil. 3. Imaging, morphology. All three need to click for an anomaly to persist. So far, 2 anchors are firm size bounds from Hubble and OH from Meerkat, and the closest approach window gives us leverage on the rest. For the film's pacing, play the countdown like a calm checklist. T, 30 days. Teams finalize JWST visits within the 85 degrees, 135 degrees elongation corridor, ground IR and radio book time. Rubin brokers the alert stream. T10, cross-facility rehearsal frames to lock photometry and astrometry pipelines. T0, HST snapshots, JWST spectra, prompt alerts, and radio follow-ups arrive within hours to days, each slotting into the shared ledger. The mood isn't suspense. It's serenity, measure, compare, decide. And remember why this matters to the thesis of our story. If the volatile mix and recoil agree with A is less than or equal to 5.6 km nucleus under sunlight, the powering paradox dissolves into material science, internal plumbing, grain economics, and geometry. If they don't, the shortfall won't be a vibe, it will be a number with units, repeatable across instruments. Either way, December 19 is not an omen, it's an audit. One good spectrum could end this. If the debate is a fog, a calibrated spectrum is the sun that burns it off. One clean JWST pass that separates H2O, CO2, CO, and flags sulfur-bearing species like OCS would tell us whether sunlight plus ordinary ices can power everything we've seen, or whether the ledger still comes up short. That's not wishful thinking. It's exactly what JWST is built to do, provided the target sits inside its 85 degrees, 135 degrees solar elongation window. In December, geometry finally cooperates. The recipe is simple and testable. 1. Volatile budget, the big three. Measure simultaneous production rates for H2O, CO2, and CO. If CO2 is high relative to H2O, the same power comes from a smaller sunlit area because CO2 sublimates efficiently at larger heliocentric distances. If CO dominates, you expect even stronger activity for a given area. Either way, line fluxes convert looks powerful into numbers. JWST's moving target modes and spectrometers, NearSpec, MIRI, were designed for exactly this sort of solar system chemistry under the elongation constraints above. 2. Cross-check with radio, water proxy. Repeat the 18 cm OH detection that Meerkat already delivered to track temporal variability and tie radio-inferred H2O to JWST's infrared water lines. Narrow OH at 1,665. 1,667 MHz is the photolysis fingerprint of ordinary cometary water chemistry. Not a transmitter, so a matched radio, IR budget, removes a whole class of rumours in one stroke. 3. Astrometry hears the thrust. High-precision positions across the window should expose any non-gravitational acceleration required by the outgassing. If the mass loss rates implied by spectra demand a sizable rocket effect, the orbit fit must show it. If the fit stays quiet, the claimed thrust anomaly weakens. Rubin, LSST's alert ecosystem, and cadence help synchronize follow-ups and keep residuals honest. 4. Morphology that matches physics. Hubble rechecks the silhouette under better phase angle, a single central condensation or not, jets versus debris texture and brightness profiles to feed dust models. Its earlier work bounded the nucleus at is less than or equal to 5.6 kilometers, possibly much smaller. Pairing that size frame with new line-by-line production rates closes the small tank, big plume argument on evidence rather than aesthetics. How, precisely, could one good spectrum end it? If H2O, CO2, CO production rates, plugged into a standard thermal model, pay the observed light bill, and match the non-gravitational term in the orbit, the anomaly dissolves. Sunlight plus vents suffice, with internal fracturing, hidden active area, as a plausible detail, rather than a deus ex machina. The OH line already anchors the engine to water chemistry. If, after we do that math, a shortfall remains, it won't be a vibe. It will be a number with units xkg, S missing, repeated by independent teams. That is how models break in comet science. On the page, under cross-instrument audits, not in thumbnails. We should also be clear about what a spectrum won't do. It won't by itself prove or disprove microfragments inside the coma. For that, you still need deep imaging and, ideally, polarimetry to constrain grain sizes. But it will box the problem. A high CO2 H2O ratio pushes us toward natural efficiency. Modest totals push us toward a larger, effective, active area. Any extreme would have to echo in the orbit residuals, or it doesn't count. The cultural contrast is deliberate. Weeks of what if gave us noise. The O detection gave us a voice we can parse. JWST and Hubble give us the grammar to finish the sentence. Keep the discipline that got us here. Institutional nucleus bounds. Hubble, ordinary anti-tail physics for sunward spikes, Finson Probstein Sekanina. If morphology tempts us, and radio lines that already said water, the rest is bookkeeping hard numbers, no adjectives. When the window opens, we aim for a three-lock agreement: spectra, plus astrometry, plus imaging. If all three click, the narrative settles with technical grace. If one refuses, we'll know exactly where to look next, and why. Either way, this is the calm part of the film, the countdown, where instruments, not opinions, get the last word. NASA has them, but we don't. From Mars, the geometry was perfect. ESA confirmed that its Mars-orbiting spacecraft, Trace Gas Orbiter, and Mars Express turned toward 3I, Atlas, between October 7, 2025, when the comet skimmed past the planet. Public posts later highlighted that October 3 was the closest pass. Those vantage points are on the record. What isn't on the record yet are the high-rise frames everyone is asking about. Multiple outlets and blog posts claim that the high-rise camera on NASA's Mars Reconnaissance Orbiter imaged 3I, Atlas, around October 23, 2025, but that the images have not been released publicly. Futurism summarized this plainly. High-rise captured the interstellar object. The public hasn't seen the pictures. I cannot confirm this from an official high-rise NASA release. The high-rise catalogue does not presently show a public 3I, Atlas, product. Timing fuels the frustration. NASA's own operating status page confirms the agency reopened on the 12th of November 2025, following a funding lapse. Commentators, including Avi Loeb in a widely shared post, explicitly tied the release delay to the government shutdown, pressing NASA to publish 4 zero-day-old high-rise images. That is their claim. What I can confirm: the shutdown happened, and NASA resumed operations on November 12. I cannot confirm that the shutdown is the official reason the images remain unreleased. NASA has not issued a detailed cause in a primary statement we can cite. This is where public science meets public patience. Planetary data normally flow through vetted pipelines, calibration quality checks archiving. In a shutdown, non-essential processing and public-facing releases can pause. After reopening, teams triage backlogs. The tension is obvious. An interstellar target is ephemeral, and open access lets independent groups model geometry, dust, and jets in parallel. Newsrooms have amplified the pressure to release narrative again, without an official NASA high-rise memo explaining the delay. The fairest reading today is: reports point to unreleased high-rise frames from Oct 23. The agency reopened Noved 12. The causal link has not been officially confirmed. Why those Mars-side images matter for our film is simple. A high-rise cut at tens of meters per pixel could check the single condensation versus fragments question from a different line of sight. constrained jet angles independent of Earth's anti-tail projection. Anchored dust, geometry models run with ESA's TGO glimpse from the same week. That's not politics, it's method. Cross-vantage data either reinforce the natural anti-tail reading and intact silhouette, or they don't. ESA's TGO has already posted a low-signal closest view clip. Higher-resolution high-rise frames would close the loop. Until they're public, we're working with asymmetry, a verified Mars-side look from ESA, and a widely reported but not yet officially released set from MRO, high-rise. So we keep the tone disciplined. Verified. Mars-side observations occurred. Oct 1, 7 ESA. Closest approach near Oct 3. NASA reopened on November 12 after a shutdown. Reported, not yet confirmed by a primary NASA, high-rise release. High-rise imaged 3I, Atlas, Oct 2-3, and has not released the data publicly. I cannot confirm this from a primary archive page. Multiple secondary sources say it happened. Implication. Public release would materially improve model constraints in the powering debate by adding a second, near-simultaneous vantage. That's why the community keeps asking. Until those frames land, the best use of our breath is to show the audience how to self-verify. Link ESA's posted Mars-side context. Note NASA's status update. Watch official high-rise channels and the planetary data system for a dated product and caption, not screen grabs of headlines. When they publish, well, incorporate them like everything else here, as measurements with provenance, not rumors with magnetism. It formed around another star. Begin with the unromantic word that makes the rest possible. Hyperbolic. A body bound to our sun moves on closed ellipses. A body from elsewhere skims through on an open curve, the energy sign refusing capture. That's what 3I, Atlas, carries in its math, an interstellar trajectory, and Hubble's brief portrait of a teardrop coma around a small nucleus sets the scale of the traveler we're discussing. A solid core, no larger than 5.6 kilometers, possibly much smaller, wrapped in ordinary dust. It is not ours, it never was. It came from a different nursery, and it will leave. We know interstellar visitors are real because they've already knocked on our door. The first, 1I, Oumuamua, arrived quietly and left loudly, no visible coma, a non-gravitational nudge in its path, and an argument that still hasn't cooled over whether sunlight pressure or unseen outgassing did the pushing. The second, 2I, Borisov, obliged with an obvious coma and tail, and then with chemistry that did not look like home. ALMA measured carbon monoxide at 9 to 26 times the typical solar system comet abundance, implying formation in a furnace of cold temperatures below 250 degrees Celsius, where CO ice piles up like snow in the dark. Together, they sketched a message. There is more than one way to build a comet, and other systems rehearse recipes our own didn't use. 3I, Atlas, is the third line of that message, this time written with a size we can imagine and a radio voice, 18 cm OH, that says the engine is sunlight cracking water. Origin is not a postcard. It's a probability. In other circumstellar disks, young, gas-rich, disorderly planetesimals accrete, collide, and, as giant planets migrate, millions are scattered outward onto unbound paths. A sliver of those wanderers crosses the sun's sphere of influence each century, most unseen. What pushes a few into the thin slice of sky our surveys watch is geometry and luck. What lets us recognize them is the same detail that made 3I unmissable. The orbit's energy and orientation refuse every bound fit. Newsrooms shortened that honesty into third interstellar object. The underlying truth is practical. This is a sample of somebody else's building material on loan. The differences matter because the similarities lull. 3I, Atlas, draws a familiar silhouette coma, tail, and then keeps telling you it did not grow up here. Dewitt and Luce pre-perihelion NOT campaign found optically dominant grains around to 0.1 millimeters, ejected slowly to 5 meters per second, a dust regime that happily explains the stubborn anti-tail geometry we later saw and also echoes a detail from 2I, Borisov, a penchant for large grains. The heliocentric brightness law they derive sits comfortably within the zoo of solar system comets, while independent spectroscopy in 2025 flagged an unusually CO2-rich coma for 3I. In combination, those clues suggest an object whose interior plumbing and volatile mix are tuned by a nursery that was colder, for CO, or simply evolved differently, for grain cohesion and size. The accent is subtle, but it's there. What does formed around another star do to ice? In the young belts beyond exoplanet snowlines, temperature gradients carve chemistry into stone. CO condenses only where space is bitter. CO2 at warmer rings. H2O closer in. If a disk's pressure bumps trap pebbles efficiently, dust aggregates grow fluffy and large. If radiation and turbulence are harsh, surfaces sinter, pores seal, volatiles hide deeper. Borisov's extreme CO content practically screams born in a freezer. If 3 is confirmed CO2 richness holds, it points to a different shelf in the same cosmic pantry, a place where CO2 ice was plentiful and the dust managed to grow big and hang together. The fact that 3 is visible light dust evolution, sun-facing fan to antisolar tail, can be modelled with big grains that respond sluggishly to radiation pressure, is less a quirk than a fingerprint, a material memory from another star's outskirts. Our instruments do more than admire. They translate accents into numbers. Hubble constrains size and confirms the way only relentless astrometry can, that the path is unbound. Webb separates molecules and, by doing so, assigns the powering bill to particular ices. Radio arrays like Meerkat listen for O8, the photolysis fragment of water that turns its active into its water. Each of those tools lifts the story out of metaphor. Interstellar stops being a headline and becomes a column in a table of abundances, grain sizes, production rates, and non-gravitational terms. Cosmic humility begins when you accept how little of this traffic we actually sample. Before Pan-STARRS and Atlas, 1I and 2I might have slipped by unannounced, before Rubin Vera C. Rubin Observatory. Our census of faint, fast movers was a polite shrug. Forecasts for Rubin's survey cadence suggest detections of order 1 small interstellar object every couple of years, maybe more, as techniques sharpen enough to turn anecdotes into a population, enough to test whether Borisov-like chemistry is common and whether Oumuamua-like oddities were inevitable or rare. In that light, 3I is not an end. It is the first member of a class that will finally be numerous enough to compare. There is a paradox in interstellar comets. Each one is an exile that tells you something about home. If 3I is CO2, leaning and dust large, it hints at formation zones and disk physics in its natal system, pressure bumps that trapped pebbles, an irradiation and temperature history that preserved certain ices, perhaps giant planet rearrangements that hurled it outward. If its OH line varies with solar distance in step with ordinary sublimation, then sunlight is doing exactly what it does to our own comets. If its non-gravitational tug ends up modest and consistent with the measured volatiles, then even this visitor's strangeness will sit comfortably inside the rulebook. In both outcomes, the universe feels bigger, not smaller. We should also say aloud what Interstellar does not license us to do. It does not let us drag every mystery into science fiction. NASA's briefings and mainstream coverage have been explicit. 3I, Atlas, behaves like a comet. And the detections so far, Hubble imagery, O8 radio line, lands squarely in natural physics. Debate is good, measurement is better, adjectives are last. The discipline we've shown, separating anti-tail geometry from propulsion fantasies, labeling personal calculations as such, asking for spectra and astrometry to arbitrate belongs to the humility chapter as much as to the methods one. What remains is the human part, and it too has a cadence. Light, silence, memory, breath. Light, a smudge from another sun, hardens into a comet with a tail. Silence. Solar conjunction swallows it and forces us to wait. Memory. Hubble frames, not logs, and radio lines stack into a chronology we can defend. Breath. A December window where instruments, not opinions, speak. In that rhythm, formed around another star stops being a boast and becomes a posture. We look up, we measure, we let the numbers be larger than our hunches, and when 3I leaves, and it will, the best thing we can do is be ready for the next arrival. Rubin will widen the sieve. JWST will still be warm and listening. New mission concepts, Comet Interceptor today, bolder pursuers tomorrow will wait at Lagrange points to spring. When an inbound track clears the threshold, we will meet more exiles. Some will be dusty and plain. Some will carry chemistry that redraws our tables. One or two may stubbornly refuse our neat boxes and force new ones into existence. That's the promise hidden inside a hyperbola. The sky is a crossing place, not a fence. For a film about powering, this chapter is the softest and the most exacting. The softness is in the admission that we are provincial, that our rulebook was written in one neighborhood of one galaxy, and that other neighborhoods will keep amending it. The exactness is in how we carry that admission, with receipts. Hubble bounds the body. JWST weighs the breath. Radio hears the water. Dynamics hear the push. Dust models explain the sunward trick. When we say another star, we mean a bound on the nucleus, a sign on the orbit, a spectrum with lines. The wonder that chooses evidence is still wonder. It just lasts longer. We solved nothing, but we mapped the questions. Start with the receipts we can stand on without flinching. The orbit is interstellar hyperbolic, inbound and outbound. No bound fit survives the math, and Hubble set the size frame early. A nucleus no larger than to 5.6 kilometers across, possibly as small as a few hundred meters. That's our tank before we argue about any engine. It's not ours. It never was. It's passing through. Next, the season's hard pivot from rumour to chemistry. South Africa's Meerkat array heard narrow hydroxyl lines at 1,665, 1,667 megahertzes, the 18 cm OH signature that appears when sunlight photolyzes water in a comet's coma. Newsrooms framed it carefully. First radio signal from 3I, Atlas, and not aliens, just water being split by sunlight in a natural outgassing process. That single detection moved the discourse from what if to what is. We also have the control case for what fragmentation really looks like in this same sky. C 2025 K1 Atlas did shatter. Sequences show multiple condensations after its solar brush. That's what debris shouts like. Put those frames beside the mid-November, looks at 3I, Atlas, one central condensation plus structured dust, and you get a baseline contrast. One comet that yelled broken, one that didn't. Keep that contrast in your pocket for later. Geometry got untangled too. The sunward spike that seemed to aim at the sun, our season's optical villain, belongs to the anti-tail literature that's older than most of us. Finson-Probstein dust dynamics and Sekanina's follow-ons explain sunward sheets as perspective, plus large, slow-responding grains near the orbital plane. It looks rebellious. It's textbook. If you've never read those models, this year forced you to. Mars gave us a second vantage and a lesson in public patience. ESA's Trace Gas Orbiter and Mars Express turned toward 3I, Atlas Oct 17, with TGO capturing a closest view, yet GIF, on Oct 3. That's posted and citable. The missing piece is NASUS, rumoured high-rise cut. Multiple outlets say MRO. High-rise imaged the comet around Oct 23, but never released the frames, with some blaming the U.S. government shutdown that ended November 12. What we can confirm, ESA's TGO images exist. NASA did reopen on November 12. The causal link explaining the high-rise delay has not been stated in an official high-rise NASA release we can cite. So, we hold the line, reported, not confirmed in a primary archive. Those are the pillars. Everything else is a mapping exercise, what fits inside them cleanly and what still squeaks. What fits cleanly, natural comet physics can look louder than it is. Images are seductions. Big grains dominate brightness and sculpt tails in ways that feel like thrust. Anti-tails, fans, and long plumes all exaggerate power to the eye unless you model grain sizes, ejection speeds, phase functions, and viewing geometry. That's why comet dynamicists flinch when anyone converts a single dramatic still into a mass loss rate with 3 heroic assumptions between. The literature warns you. Finson-Probstein is first order. Dust parameters can move inferred production by orders of magnitude. Our season honoured that warning. What fits cleanly, outgassing can accelerate a nucleus without breaking it. Rosetta turned this from a classroom concept into measured force and torque on 67p. Sublimation produces non-gravitational terms in the orbit and spins the body with magnitudes that track season and vent geometry. That precedent is our brake pedal. Whenever acceleration becomes a synonym for engine, it isn't. It's sunlight plus plumbing, unless spectra and orbit fits say otherwise. What fit cleanly, interstellar is no longer a trophy word, It's a population in waiting. Oumuamua whispered weird. Borisov shouted, CO. 3I, Atlas, carries its own accent. With Rubin Observatory coming fully online, detection forecasts move us from anecdotes to statistics. Papers estimate anywhere from one small ISO every couple of years under conservative assumptions to dozens a year, if nature is generous and pipelines are tuned. The spread is wide, the direction is firm. Our exiles are going to become a dataset. Now the squeaks, the mapped questions that make Section 20 honest. Q1. Does the energy ledger close with ordinary ices? The OH line says water is in play. Early JWST, ground IR hints, and expert commentary suggest a CO2. Rich coma for 3I, Atlas, mirroring how 2I, Borisov's CO excess, revealed a freezer-born origin. If December spectra show H2O, CO2CO production rates that, when plugged into a standard thermal model, pay the observed light bill and match any non-gravitational term in the orbit, the small tank, big plume paradox dissolves into material science, fractures, and grain economics. If the ledger stays short by a factor you can't hide in modelling, the anomaly hardens with units, not vibes. We don't have those December numbers yet. That's the truth. Q2. How large is the rocket effect, really? Avi Loeb's essays argue for very large mass loss and thrust sometimes billions of tons per month, even tens of % of the nucleus, over a narrow window derived from morphology and assumed vent speeds. Critics point to geometry, grain biases, and note that such a strong push must leave a loud signature in the orbit, residuals, and often in spin torque. The scoreboard is ready. Spectra for rates, astrometry for recoil, light curves for spin. Until those are cross-tied and peer-analyzed, those big numbers are intriguing, public calculations, not consensus. Q3. Did it fracture inside while staying whole outside? Rubble pile nuclei, weak and porous, can replumb internally under perihelion stress, multiplying effective active area while the outline remains single core. That hypothesis would explain persistent activity without debris. It is plausible and testable line rates that exceed a smooth shell expectation, rocket terms that match those rates, spin changes without shard trains. Today, we lack direct evidence for internal fragmentation in 3I Atlas. December's cross-checks could nudge the scales. I cannot confirm it yet. Q4. What did Mars actually see at high resolution? ESA's TGO gave us a context view. If NASA's high-rise frames exist and get released, they can answer single condensation versus subtle splitting from a different line of sight and feed dust models that reduce ambiguity about the anti-tail sheet. The shutdown ended on Nov 12. The release has not appeared on a primary high-rise page as of this writing. The tension isn't a conspiracy, it's cadence. Still, second vantage data matter, and the community is right to ask. Q5. What does interstellar mean chemically, beyond headlines? Borisov's CO excess, 926 times, typical solar system comets, told us how cold its nursery was below, negative 250 degrees Celsius, for CO to pile up. If 3I, Atlas, lands with a high CO2, H2O ratio that points to a different shelf in its natal disk, with pressure bumps and irradiation histories unlike our own, formed around another star becomes lab work, abundance tables, ice stratigraphy, grain cohesion, and, eventually, population statistics from Rubin. That program is bigger than any single object, and 3I sharpened its outlines. Between those questions run a dozen narrow threads we didn't ignore, but refused to elevate. Claims of explosions have not survived observations. Claims of transmissions were pinned to chemical lines that do not modulate or drift like beacons. Claims that no tail equals unnatural evaporated, once geometry and sensitivity were accounted for. This is not cynicism, it is the choreography of skepticism. You check the bright rumor against a darker, quieter instrument, and if it doesn't show, you put it down. So what did we actually learn in the sense of changed our priors? We learned that images alone are unstable ground for energy accounting. The same frame that looks like a thruster points, in the literature, to large grains and an orbital plane sheet. Antitail 101 is no longer optional reading. We learned that a single, narrow radio line can deflate a month of rumors. O at 18 centimeters is the sound of water, and once you hear it, the space of plausible engines collapses to sunlight, vents, and ice unless proven otherwise. The next time someone says radio, ask for the line, the rest frequency, the Doppler frame, and the line width. It changes the temperature of the room. We learned that a control comet is worth 10 debates. C. 2025. K. One reminded the public what fragmentation looks like in pixels. By contrast, 3I, Atlas, did not present those signatures in widely reported frames. That 1 week juxtaposition restored sanity to the "did it blow up" chatter without us having to raise our voices. We relearned, from Rosetta's ledger, that non-gravitational forces have manners. They show up in orbits and in spin, in seasonally modulated ways that you can model and test. If December's fits demand only modest Marsden parameters, that will be the end of the outsized thrust story. If they demand more, we'll have the spectra to check whether the gas can pay the bill. Either way, the test is mechanical. We also drew a bolder outline around the public science contract. ESA's rapid TGO release modeled transparency under constraint. The U.S. shutdown showed how even routine data products can bottleneck at the worst narrative moment. The correct posture isn't outrage, it's insistence, time-stamped releases, captions with geometry and instrument modes, and a link to a permanent archive entry the public can read. If you want a rumor to die fast, publish early and completely. And we put the next steps in a checklist where anyone can follow. December 19 isn't a prophecy, it's an audit. What we still don't know, the true size of the non-grav term, the volatile mix in numbers, any subtle morphology changes, is exactly what HST, JWST, ground IR, radio, and global astrometry are designed to answer when geometry is kind. The cadence is simple: spectra for rates, astrometry for recoil, imaging for silhouette. 3 locks. Either they click or they don't. The rest are adjectives. If the locks click ordinarily, 3I, Atlas, becomes a case study in how strange-looking is not the same as strange-powered. Internal fracturing, plus a CO2, helped budget, and large grains could explain the persistence, the anti-tail, and any modest rocket term without leaving the rulebook. If they refuse to click if rates are too small, recoil too large, and morphology too tame for the ledger we keep, then the anomaly will be a number sober enough to survive peer review. Either outcome is good science. We end where we began: light, silence, memory, breath. Light gave us a Hubble silhouette and a Mars side dot. Silence erased the comet for 2 weeks behind the sun, and then broke in a narrow radio line. Memory kept the control comet, K1, on screen when the internet wanted explosions. Breath slowed the edit until December, when the instruments, not the adjectives, carry the argument. We didn't solve it, we drew the map. Interstellar, small tank, HST, check. Water chemistry speaking on radio, meerkat, check. Anti-tail as geometry with big grains, Vinson Probstein. Seconina, check. Real fragmentation looks like K1, and this wasn't it, so far, check. Open tests left for December. Spectra recoil silhouette pending. If you wanted a verdict, you'll be disappointed. If you wanted a way to watch along with a scientist's calm, you've got one. The path from we solved nothing to we solved the right thing is a ledger, not a leap. Whatever happens next, we saw it. There's a moment every observer knows that has nothing to do with equipment. The dome is open, the motor hum fades into a long, patient, quiet, and a dim thing you've chased for weeks finally slips into the field. It isn't bright, it isn't noble, it's a grain of ash drifting through the cold. But then it does what only the sky can do. It rearranges you. We watched first through noise, then through knowledge. We watched a smudge harden into a visitor, and a visitor turn into a question, into several questions, into a whole room of arguments that somehow never spoiled the silence. Light found it. Silence grew around it. Memory began to stack frames, dates, plots, a radio line no one could shout over, and breath, always breath, measured out the waiting and the work. Maybe that's the legacy already written, not a verdict, but a choreography, to care enough to ask the right thing, to hold your posture when rumors spread, to use words like yet and so far as if they were safety gear, to refuse calmly, to make the story bigger than the measurements, and discover, as you persist, that the measurements are already bigger than the story. It turns out a hyperbola is a kind teacher. Everything about it says, "This is not yours." It enters without promise and leaves without apology. There are no sentimental orbits, no cozy returns. You get one pass, maybe a few half-clean looks, and the rest is a ledger. What you saw, what you didn't, what you can prove. And yet, inside that austerity, a tenderness sneaks in. You catch yourself rooting for a rock to hold its outline. You find yourself whispering stay to a smudge that has never once heard English. You keep the vigil anyway because keeping vigils is how we remember we're capable of care at a planetary scale. What did we learn from that? Not a tidy theorem, maybe, but a usable courage. The kind that lets you take an image that looks like a thruster and say, "Give me geometry." The kind that hears radio and asks, "Which line?" The kind that can look at a wave of certainty and answer with a sequence of instruments. If there is wisdom in a comet, it's this. Don't confuse the dramatic with the decisive. The decisive is usually narrow, often quiet, and always patient. The decision doesn't need your adjectives. It would be easy to wrap everything in meaning that the object was never intended. We could turn its path into an omen, its tail into an arrow, its stubbornness into an allegory. But the older truth is cleaner and harder. Curiosity is the point. The act of looking is the first ethics. Not in the sense of snoop or claim, but in the discipline of attention, of showing up with enough humility to let the world be itself and enough craft to hear what it's saying. Curiosity is how we keep faith with a universe that never promised to be legible. There's also the smallness to honor. The human scale in all this isn't a headline. It's a night shift. Somebody set the alarm. Somebody checked a weather page and drove anyway. Somebody aligned an instrument, recalibrated after the air changed, nudged a focus wheel as if the cosmos was sensitive to grace. Somebody wrote a log entry with hands that ached. Somebody brewed coffee and kept the door propped with a plastic wedge that has outlived 3 computers. The greatest truths we learn at galactic distance are often carried home by people who are just good at their jobs. And there's the bigness to honor, too. The way public science can be a kindness. The way a posted frame with a real caption can quiet 10,000 confident strangers. The way a shared curve, no drama, just data, can put a world back on its feet. We sometimes talk about transparency as if it were a virtue reserved for saints. Here, it's a method reserved for adults. You publish early if you can. You annotate with care. You accept the correction when it comes. And you forgive the delay when the machinery that serves you falters. The goal isn't to win an argument, it's to let reality carry more of the load than your theory does. If you're still listening, you may notice how the film has moved. We opened with the thrill of a contradiction. It should have shattered, but it didn't, and took a breath long enough to separate comfort from confirmation. We cut from rumor to radio. We split a sunward spike into vectors and dust. We used a broken cousin as a control, not a punchline. We let a scientist with a loud pen sharpen our questions without letting his italics replace our instruments. We kept the most daring possibility in sight, a world that doesn't quite fit the rulebook, while refusing to skip the pages it would have to crease. That's not indecision. It's craft. It's what you learn to love after you've chased a few comets and nursed a few disappointments, and realize that the relief you feel when numbers close is a better high than any twist you could have written. The sky can be generous. It can also be literal. If you are lucky, you come to prefer both. Will we get the spectrum that ends the debate? Maybe. Maybe not. Perhaps we'll get 3 that lean the same way, and someone, somewhere, will write consistent with and smile, a private smile, because consistent with is our kind of poetry. Perhaps the orbit fit will need a small nudge, and the chemistry will pay it without overdraw. Perhaps a deep image will show a second condensation after all, faint and dutiful, and well adjust the captions and mean it when we say new information. Perhaps a Mars side frame will slide quietly into an archive and not change anything, and it will still be worth it because we will know. Or perhaps the shortfall will survive the audit measurable, repeatable, not interested in your comfort. If it does, nothing breaks. The world simply becomes more specific. Our next chapter won't be titled Alien or Engine, because that's not how knowledge moves. It will be titled with the missing units and the instruments that found them. We will then invent better questions and build the tools they require, and a decade from now, some smaller version of you and me will We'll tell this story in the past tense, and we will realize, again, that boredom is a luxury the universe still won't let us afford. There are practical echoes to carry out of the theatre. We can keep the checklists that protected us from ourselves. 3 locks, spectra, astrometry, imaging. We can keep the habit of using control cases as our grammar, not our decoration. We can keep the instinct to stamp provenance on every image before we let it touch our beliefs. We can keep the kind of patience that has a calendar and an alarm, not the kind that drifts into fatalism. We can keep the courage to admit, I don't know on camera, not as a shrug, but as a promise. And this matters. We can keep writing scripts that make room for quiet. The internet has trained us to stand on chairs. The sky has trained us to sit back down. R is not a stunt. Wonder doesn't need a cymbal crash. Sometimes, the most honest thing you can do when a question is still working is light the frame correctly, let the numbers speak in whole sentences, and leave the door open a little longer than your schedule prefers. What will the visitor remember about us? Nothing about, of course. It didn't aim. It didn't choose. It never turned to look. The watched back in our title isn't about intent. It's about consequence. We projected our care onto a thing that cannot return it, and became, in the act, a little more worthy of the care we keep asking from each other. We built an archive that a child can read when we are no longer here to insist on our part in it. We learned to disagree at speed without discarding the premise that reality is a shared room. We are not the first to learn any of this. Centuries of skywatchers discovered the same rhythms with weaker glass and braver guesses. They, too, wrote columns of numbers on hard nights and tried to decide which were noise and which were news. They, too, got fooled by geometry and learned to love it. They, too, waited for a spectrum that a cloud decided they didn't deserve. If there's comfort to be had, it is not in novelty, but in continuity. We are temporary. The work is long. The universe is patient. Our best way to honor both facts is to become patient in a way that outlives us. When the credits roll, let's leave differently than we arrived. Keep the motif in your pocket, not as a trick, but as a way to travel. Light, give it the right glass, the right questions, and the chance to say more than your excitement does. Silence, use it as a practice, not a performance. Let waiting become part of the method, not a gap in the story. Memory, write clean captions. Keep your files boring and complete. Link what you learn to what you can cite. Make it easy for strangers to trust you. Breath pace yourself like the sky paces us. Every 30 seconds, a new point of view. Every act, a humility we were not born with, but can rehearse until it feels like home. We watched. It watched back in the only way the universe ever does. By existing, by refusing to perform, by allowing us to find an order that is not our invention and to be reshaped by it. Whatever happens next, a spectrum that clicks, a curve that bends, another visitor already inbound, where the deep background looks slightly wrong, we have the one thing that matters most in this kind of work. We were present, and we made that presence precise. Let the last beat be soft. Let the comet go where it was already going. Let the instruments close their eyes. Let the logs settle like silt. Somewhere, out past the cold blue of Neptune's crawl, a dim thing we cannot name yet is already on its way, already older than any question we will attach to it, already indifferent and perfect. We will meet it with the same posture we finally learned to keep: wonder without agenda, vigilance without panic, expertise without arrogance, and a kindness for the truth that does not need us but keeps choosing, somehow, to include us. Whatever happens next, we saw it, and we will be ready to see again.